So here we've got a system of 4 equations and 4 unknown variables. And if we want to solve this by the Gauss-Jordan method, we start by putting it in an augmented matrix. And how would we build that matrix? What numbers are we going to use here?
By the first row, it would probably be 1, 1, 2, -5.
Yeah, we can just pull those coefficients. And then what else?
And then put like the long line and then a 3.
Yeah. So 1x plus 1y plus 2z minus 5w equals 3, using essentially place value instead of the written variables. And then we can do the same thing for the others. We can just take the coefficients, 2, 5, -1, -9. And then equals -3. And same thing for the other rows. Coefficients, 2x plus 1y minus 1z plus 3w equals -11. And 1x minus 3y plus 2z plus 7w equals -5. And we want to row reduce this ideally all the way to row reduced echelon form. And to do that, what would be a good first step? What are we trying to accomplish here?
We make everything under the 1, 0.
Yeah, because we do have a 1 in the top left, so we can treat that as our first pivot. So in the first row, our first non-zero number is this 1 here. So we're going to call that the pivot, or a pivot. And that's already a 1, which is good. If it wasn't a 1, we would eventually want to make it a 1, but that can be done as a last step. The important thing is we want to reduce everything in the same column. So how could we get rid of this 2, for instance? What change could we make?
We multiply the top row by -2.
Yeah, and then add that to that second row. Note that we don't actually need to change the first row at all. We're just using the first row to change the second row. So we're going to modify row 2 by adding -2 times row 1. And let's see what that looks like. So first row, we're keeping exactly the same. Second row, we're modifying. 2 plus -2 times 1 becomes 0. 5 plus -2 times 1 becomes 3. -1 plus -2 times -2. So we've got -1, we're adding -4, we get -5. -9 plus 10 from the -2 times -5 becomes +1. And also, since these aren't zeros, we do need to keep track of them. -3 plus -6 becomes -9. So that's our new second row. Any questions on that so far? And while we're at it, even though this is technically a next step, we can combine them all into one step. How could we modify row 3 to get rid of this 2? Yeah, we could do the same thing. We can add -2 times row 1. And by the way, there are other ways to do this. You could, for instance, modify row 3 by just adding -1 times row 2, or -2 times row 4. So there are many ways to row reduce a matrix. They will all eventually lead to the same row reduced echelon form, but there are many ways to get there. However, it is useful to have just a standardized method to take all the guesswork out of it. So as a standardized method, and this is what we usually call Gauss-Jordan elimination, we start from the top and work our way down using higher rows to modify lower rows one at a time. So let's see what that works out to. What do you think these numbers are going to be based on this operation? What do we get as a result there?
The first one would be 0.
Which is exactly what we want.
And then the second one is 1 plus.
We've got a 1 and we're adding -2 times this 1. So yeah, that'll be -1. And then -1 plus -2 times 2 results in what?
1 plus -4,
-5, because we're adding -4. And then 3 plus -2 times -5. We're adding, what's -2 times -5 going to be?
10,
So we're adding that 10 to 3.
13.
Yeah, so we get a 13 there. And then -11 plus -2 times 3.
-6 plus -17.
Yeah, sounds good. And so we've eliminated the numbers under the pivot. We still need to get rid of this 1 here. So what operation will work for that? What should we add to this row?
Negative row 1.
Yeah. We don't even need a multiplier beyond -1 because the 1 will be canceled out by -1. So we're ultimately just subtracting 1 minus 1, -3 minus 1, 2 minus 2, 7 minus -5 becomes 7 plus 5, and -5 minus 3. So that's our modified matrix. Any questions on those first steps now that we've got that pivot alone in its column? And what's our next pivot?
We get the 5 on the second row to be a pivot. Is that what?
Not quite, because pivot means the first non-zero you encounter in the column or in the row.
Oh,
Yeah, it should be if we go from left to right, we've got this 1 here. That's a pivot because it's the first non-zero we encounter in the column. And it's alone in its column, or in the row, as we read from left to right, and it's alone in its column. In the next row, as we sweep from left to right, what's the first non-zero number we encounter?
3.
Yeah, so that means this 3 is the pivot. So we would want to use this 3 to eliminate everything above and below. So by the strict Gauss-Jordan method, that would be the next step. We would use this 3 to eliminate the 1, the -1, and the -4. So for instance, what multiple of 3 would cancel out a 1?
So where we add it to -3.
Well, what would you have to multiply 3 by to get something that cancels out a 1? 3 times what would cancel out a 1?
1/3.
Yeah. So we could multiply this whole, or we could add -1/3 times the second row to the first row. So that's what would be the next step based on a strict interpretation of this procedure. The problem is, although that works, it's going to lead to some numbers that are kind of annoying to work with. Because the 3 times -1/3 just becomes -1, which cancels out the 1. But the -5 times -1/3 becomes 5/3, which adds to the 2, and we're going to end up with some messy fractions. It's absolutely possible, but in terms of actually writing it out by hand, it gets pretty tedious. If I were programming a computer to do this, this is the method I would use. I would want that because computers have a really easy time dealing with decimals and fractions and stuff, but a really difficult time thinking through, well, should I do this or this, making choices like that. So if I were making a computer program, I just have one unified method that works every time, even if it leads to some messy numbers. But doing it by hand, I would say I don't want to mess around with those complicated fractions. But if I look elsewhere in the column, there are some other numbers that are going to be much easier to work with. So it's often worthwhile to explore what other numbers could you use instead, because the order of the rows doesn't really matter. Why are the rows in this order in the first place? Or the rows of the original matrix? Why were they in this order and not some other order? Like, why did we write this as the first row and this is the second row and this is the third row? Yeah, that's how they were listed in the original system of equations. This row was the coefficients of the first equation. But in a system of equations, does it matter which order we list the equations in? It shouldn't, right? If we swap two of the equations, it's still the same system of equations. It's still the same information. And likewise, if we're just using this augmented matrix to represent a system of equations, it doesn't matter what order we list the rows in. We can swap rows around freely, and that doesn't change the information. So we could swap this row with another row that's going to be easier to work with. For instance, if we swap with row 2, or we'll swap row 2 with row 3, then we'd have a -1 here. And a -1 is going to be much easier to work with because you can just multiply it by nice, neat whole numbers and not have to worry about the fractions. I think we might be even able to go even easier though, because even though a -4 doesn't look easier than a 3, what do you notice about all the numbers in this row?
The multiple of 4s.
Yeah, those are all multiples of 4. So instead of using the 3 as a pivot and using 1/3 and 2/3 or whatever to eliminate everything else in the column, let's do a row swap and get rid of that 4. So to make things easier, let's multiply this entire row by, ultimately we want the pivot to be what sort of number? Yeah, we want the pivot in the end goal to be 1. So let's multiply this whole row by -1/4. And while we're at it, let's switch row 2 and row 2 and the modified row 4. So we're going to be doing 2 steps at once. We're going to multiply all of row 4 by -1/4 to make the numbers easier to work with, because they're all multiples of 4 anyway. And we're going to swap that modified 4th row with the second row. So let's see what that looks like. First row, we're not changing. The second row is going to get replaced with -1/4 of the 4th row. So we're going to take -1/4 times everything in the 4th row and put that in the new second row. So 0 times -1/4, -4 times -1/4 is just 1. That's what's going to make this much easier to work with. We now have a 1 as a pivot. 0 times -1/4 is 0. And the presence of this 0, I think, is also going to make the next few steps much easier. That's a good thing to watch for. If you can find a row with a 1 in the place you want and a lot of zeros, that's going to be much easier to work with. And then 12 times -1/4 is -3. -8 times -1/4 is +2. Third row, we're keeping exactly the same. And the 4th row, we're swapping with the second row. So the original second, or the previous second row, becomes the new 4th row. 0, 3, -5, 1, -9. So this matrix, I think, is going to be a lot easier to work with, because we now have simply a 1 as the pivot. That's going to make it a lot easier to reduce the rest of the column. And this 0 here is going to mean a lot less work for the next few steps as well. So we now have our first row has this pivot, the first non-zero we encounter in that row, reading from left to right. Second row has this 1 as a pivot, the first non-zero we encounter as we read from left to right. Any questions on those steps so far? And now we want to use that pivot to eliminate everything else both above and below. So how can we accomplish that? What operation, for instance, could we use to eliminate this 1 above it? Yeah, multiply this whole row by -1 and add it to the first row. So we're modifying the first row by adding negative row 2. And let's carry out that operation and see what we get. First row, we're going to get 1 minus 0 is 1. That doesn't change. 1 minus 1 is 0. That's our goal. We wanted a 0 there. 2 minus 0 doesn't change. -5 minus -3 becomes -5 plus 3, so -2. And then 3 plus -2 becomes 1. Second row, we can just leave exactly as it is. That's the tool we're using to modify everything else. And then the third row, what operation would change this row to get rid of that -1? What could we add to this row? Yeah, if we just add the second row exactly as is, we don't even need a negative sign because these will already cancel each other out. So we'll just add those, 0 plus 0. And it's important that this 0 isn't changing. We spent a lot of time establishing that 0. We want to keep that 0. We don't want to lose it. If there are some other zeros that happen to show up, like if we lost this 0, that wouldn't be so much of a problem. We're going to be needing to address that column later anyway. But zeros you've already established on the left side you want to keep. Then we've got a -1 plus 1 cancels out. That's what we wanted to establish. -5 plus nothing doesn't change. 13 plus -3 is 10. -17 plus 2 is -15. And then what about the fourth row? What change could we do there? What do we want to add to this? Yeah, if we add -3 times row 2, that'll cancel out the -3 or the +3 there. So 0 plus -3 times 0 is still 0. Again, we don't want to lose the 0 we've already established. 3 plus -3 times 1 is 0. Canceling that out was the whole point of this step. -5 plus nothing is still -5. 1 plus -9, so that's 1 plus 9. And -9 plus -3 times 2, that's -9 minus 6, so -15. Any questions on that so far? And what just happened? What important property does this matrix now have? Or what's going to happen in the next step? Yeah, we can, it's almost to row reduced echelon form already, right? We're going to need 1 or maybe 2 more steps. But what do you notice about the fourth row we just got?
It's the same as the third row.
Yeah, this new fourth row is the same as the new third row. And we got those in different ways. We got the third row by combining the original 4 rows in certain ways. We got the new fourth row by combining the original 4 rows in different ways. But those different combinations led to the same information. And now what can we do with the fourth row using the third row? What happens when we combine those? Yeah, those are going to cancel out to a row of all zeros. In fact, that's our very next step. We can just add negative row 3 to row 4, and the new row 4 is going to be all zeros. So the final row is going to be all zeros. And that tells us it was possible to combine all 4 rows in a certain way that resulted in a row of all zeros. Ultimately, what we've done here, if we think of the rows as vectors, let's say row 1 as a vector, row 2 as a vector, row 3 as a vector, row 4 as a vector. All we've been doing this whole time is just multiplying the original 4 rows by scalars by -2 or -1 or -3 or -1/4, and adding those together in certain ways. We just took ultimately some multiplier times R1 plus some multiplier times R2 plus some multiplier times R3 plus some multiplier times R4. And we added all those up to get what? Final row. What was the result of all that, all those linear combinations? That we added up a bunch of rows, combined rows with multipliers, and adding them together and end up with
Zeros?
Yeah, a row of all zeros. We found a way, and of course we kind of lost track of exactly what we were doing, but we could go back and reconstruct it. We could figure out exactly what we were doing with the first row, second row, third row, and fourth row of the original matrix to build this row of all zeros. There was some linear combination we just constructed that resulted in the zero vector. So we've just shown that there is a way to add up something times the first row plus something times the second row plus something times the third row plus something times the fourth row to create the zero vector. We were able to get all these rows to cancel out. Have you seen the term linear independence yet, or linear dependence?
I've heard of it.
The main idea is that if you have some vectors and you're creating a linear combination in the sense of multiply each vector by some scalar and add up the results. This is called a linear combination of those vectors, in this case, a linear combination of the rows. It's always possible to get those to add up to 0 if you use what coefficients? What C values will always make that true?
0?
Yeah, you can always get the linear combination to add it to the 0 vector if you use 0 for all the C values. But that's kind of sort of cheating. It's always true, so it doesn't really tell us anything useful about these particular vectors. So we typically call this the trivial solution. Trivial in the sense of, yeah, it's true, but that doesn't really give us much useful information. It is true that you can always get these to add up to 0 by using zeros for all the coefficients. But what we really care about is it possible to make them all add up to 0 other than just using 0 for all the coefficients? Like, could you have maybe 5 times R1 plus 3 times R2 minus 6 times R3 plus 2.5 times R4 happens to cancel each other out. And it turns out that's exactly what we've just done. We have just found some way of combining the original 4 rows to get a row that's all 0. We have found multipliers, even though we haven't explicitly listed out what those numbers are. But we could go back and reconstruct these operations and figure out some multipliers that make these add up to a row of all zeros. If that's possible, if it is possible to make them cancel out, other than just by using the trivial solution, we would say that those rows or these vectors are linearly dependent. If this can be done other than using the trivial solution, with C values not all 0. Then we say the vectors, or in this case, the rows, are linearly dependent. And this ultimately means, in this case, that one of them can be canceled out by the other ones. We found a way to use rows 1, 2, and 3 to cancel out row 4 entirely. If you can use 3 of the rows to cancel out the 4th row, or however many there are, if you can use some of the rows to cancel out one of the other rows, that means that that other row didn't really contain any unique information. This row 4 was able to be canceled out because it was just duplicating the information in the other rows. And I think that's most obvious in this previous step. The 4th row is identical to the 3rd row. It doesn't contain any new information. But that can be traced back even to the original matrix. If you take a look at these 4 rows, each of these 4 rows contains information. But one of those rows is just duplicating the information contained by the other 3 rows, which is why we were able to cancel it out. We were just subtracting the information held in the other rows, and that gets rid of all the information in the 4th row. So that's what we mean by linear dependence. We say these 4 rows are linearly dependent because they aren't really all necessary. If we had left out one of these rows entirely, we would still get the same result. And we can see that from the fact that one of those rows canceled out anyway. So the fact that these rows are linearly dependent means that one of those rows could be ignored and we'd still have all the information we need. We didn't know that from the start, but the fact that one of the rows cancels out to all zeros ultimately tells us that one of those rows wasn't really needed. So we can essentially treat this as a system of 3 equations instead of a system of 4 equations, because one of the rows is essentially gone. Any questions on that so far? As opposed to if all 4 rows really did contain unique information, if there was no way to get the 4th row to cancel out, then we would say those rows are linearly independent. Each one genuinely contains unique information. There's no way to get them to combine to 0 except by using the trivial solution where you're cheating and using 0 as all the multipliers. So that's some important terminology that's going to be showing up throughout the quarter. The idea of linear dependence versus linear independence. And the idea of, can you get a linear combination to add up to 0 by getting them to cancel each other out? Or can you only do that by using 0 as all the multipliers? So we're going to be revisiting that a lot in the future as well. But for now, let's try finishing off this row reduction. We got the 4th row to cancel out entirely. Can we use this pivot? So we got pivots here, alone in its column, and here, alone in its column. Now this pivot, we already canceled out the -5 below it. We don't need to worry about the 0. How would we cancel out this 2 up here? What operation would use a -5 to cancel out a 2? Yeah, 5/2 should work. Or actually, since we've got a 5, a -5, we want to multiply by something that turns it into a -2. What multiplier should we use here? Yeah, 2/5 should work best, because that way the 5s cancel out, we get -2, which will cancel out the +2. So we'll want to multiply 2, we'll want to add 2/5 times the 3rd row. So let's try that out. And the 3rd row, that might lead to some messy fractions in other circumstances, but it happens to be the case that the 3rd row is all multiples of 5. So the numbers are going to be pretty easy to work with anyway. We've got 1 plus nothing. Nothing plus nothing. 2 plus 2/5 of -5, that's 2 plus -2, so that's also 0. Then -2 plus 2/5 of 10. And what's 2/5 of 10? Yeah, so we're adding 4 to the -2 that's already there. -2 plus 4 is +2. Going down to 1, we're adding 2/5 of -15. And what's 2/5 of 15? So we're adding 6, or rather -6. So 1 plus -6 is -5. So that's our new, in fact, our final first row, because I think this is going to lead to completely reduced row echelon form. Second row we can leave as it is, because there's already a 0 above the pivot there. Third row, we don't really need to modify it, except what number do we want the pivot to be in the end? Yeah, we want the pivot to be a 1. So let's go ahead and multiply this whole row by -1/5. And we get 0, 0, -5 times -1/5 is the 1 that we need. 10 times -1/5 is -2. -15 times -1/5 is +3. And this is now fully row reduced. Because if you look at the pivots, first row has a pivot 1. That's 1 and alone in its column. Second row pivot is 1 and alone in its column. Third row pivot is 1 and alone in its column. And fourth row, where's the pivot in the fourth row? Yeah, it doesn't have one. The pivot is the first non-zero number you encounter in the row. If the row is all zeros, then it doesn't have a pivot. So this fulfills all 4 requirements of reduced row echelon form. Every pivot is a 1. Every pivot is alone in its column. The pivots are in order from top left towards bottom right. And by the way, it's okay to skip a column. Like maybe this column happened to be all zeros and the next pivot was here, and you zeroed out everything above and below. But you can't like backtrack. You can't have like pivot, pivot, and then go back to a pivot here. The pivots have to be in order from top left to bottom right. But if they're not, you can just rearrange the rows to make it right. And then fourthly, if there are any rows of all zeros, they've got to be grouped together at the bottom. So every pivot is a 1, every pivot is alone in its column. The pivots are in order from top left towards bottom right, and any rows of all zeros are grouped together at the bottom. So this is row reduced echelon form, RREF. That's all the row reduction we can do. This is as simplified as it can possibly get. Any questions on that so far? So now that we've got reduced row echelon form, let's see if we can interpret the results by going back to the idea of the original system of equations. If we were to rewrite each of these rows as an equation, and keep in mind the variables were x, y, z, and w, what would the first row look like as an equation?
X plus 2w equals -5.
Yeah, x plus 2w equals -5. And the second row?
Y minus 3w equals 2.
Yeah, sounds good. And then the third row?
Z minus 2w equals 3.
Yeah. And then the fourth row is all zeros. So you could think of that as 0x plus 0y plus 0z plus 0w equals 0. But that's always true anyway. The important thing about a row of all zeros is that it does not impose any extra restrictions. Each of these rows can be thought of as providing some restrictions describing how x, y, z, and w have to be related to each other. But a row of all zeros contains no information. It doesn't provide any extra restrictions on how the variables are related. It's just always true. So we can ignore that. We already know 0 equals 0. As for the 3 remaining equations, though, these tell us how x, y, z, and w have to be related to each other. And the important thing about reduced row echelon form Each pivot being a 1 means that variable is just multiplied by 1, making it easier to solve for. Each pivot being alone in its column means that variable only shows up in that equation. It doesn't show up in the other equations at all. So x only shows up in the first equation. It doesn't influence the others at all. Y only shows up in the second equation. Z only shows up in the third equation. However, W shows up in all 3 equations, or not necessarily all 3 in general, but in possibly more than one, because W does not have a pivot. So there's no restriction about it being alone in its column. However, that's fine because it means we can solve for the other variables in terms of W. So if you isolate x here, what would you get?
Equals -5 minus 2w.
Yeah. And y would equal what?
2 plus 3w.
And z?
Z equals 3 plus 2w.
So we can write all the other variables in terms of this mysterious variable w. Because x, y, and z are variables whose columns have pivots. W is a column that doesn't have a pivot. And the usual term we use for that is fixed variables versus free variables. We would say that x, y, and z are fixed variables. Or sometimes pivot variables. Because they have pivots in their columns. And those are the variables we're going to be solving for in terms of the other variable or variables. And that variable or those variables, the ones without pivots in the columns, those are typically called the free variables. There might be one or there might be several, but essentially any columns with no pivot. Those are the columns without pivots represent the variables that can show up in multiple equations. So we're going to be solving for the pivot variables in terms of the free variables. And that's what we've just done. We've discovered what x, y, and z have to equal in terms of w. And when we say free variable, we essentially mean free to be any value. You could choose any number you want for w and it will work, as long as x is -5 minus 2 times the value you chose, and y is 2 plus 3 times the value you chose, and z is 3 plus 2 times that value you chose. But w could be anything. Any real number. So this means there's infinitely many solutions. If we hadn't gotten a free variable, if we had had like 1, 1, 1, and then a 1 here also, if there had been a pivot here, that means there's only one solution. Because x, y, z, and w would all have specific numbers they'd have to equal. But with at least one free variable, you get infinitely many solutions instead. And we can write out those infinitely many solutions in a very useful format. If we write the solution in the form of a vector, x, y, z, w. We know w can be anything, any real number. So let me just make up a new variable. Let's say we call w r, where r is some real number. Then x is going to have to be -5 minus 2 times that number. -5 minus 2r. And r doesn't really have any specific meaning here. It's just a placeholder variable, or sometimes called a dummy variable, representing this could be anything. We don't care what the value is. Likewise, y is 2 plus 3w. So if we're calling w r, y is going to be 2 plus 3r. Then z is 3 plus 2r, since that's what we're calling the value of w here. And the advantage of this is we've taken a vector that has 4 unknown variables and rewritten it in a form that has only 1 unknown variable. So you could just leave the result like this. And then if you want specific numbers, you could plug in any number you want for r. For example, what would be the easiest r value to use here?
1.
Probably even easier than 1. Yeah, let's say 0. If we just say let r equal 0, then we get x equals -5 plus nothing, y equals 2 plus nothing, z equals 3 plus nothing, and W equals nothing. So this should be a solution to the original system of equations. If you plug in these values for X, Y, Z, and W in the original system of equations, that should make all the equations true. Or you could plug in 1. If you say let R equal 1, then X is going to be -5 minus 2. Y is going to be 2 plus 3. Z is going to be 3 plus 2. W is going to be just 1. So -7551 is another solution of that same system of equations. Since you could use anything, it doesn't even have to be whole numbers for W. But to generalize this, a very useful way of listing all the values at once is to split this format up into the constants, in this case, the -5, 2, 3, and also this R is probably best written as 0 plus 1R, just to make it consistent with all the other formats. We could write this as the constant terms, -5, 2, 3, 0, as its own vector, plus, and then the terms with R, -2R, 3R, 2R, 1R. Same thing, we just split it out into the constant terms in their own vector, plus the variable terms in their own vector. And if there were multiple free variables, we'd split it up into a vector for each free variable. Because now that this vector has an R in every term, what can we do with that R? Yeah, we could factor that out. Instead of -2R, 3R, 2R, 1R, we could just write it as -2, 3, 2, 1 times R. So we've now written a very useful general format for all possible solutions of the original system of equations. Every solution is going to be -5, 2, 3, 0 plus some real number times -2, 3, 2, 1. And we can also even think of this geometrically. This is a 4-dimensional vector, 4 by 1. So this is a space we can't directly visualize, 4-dimensional universe. But -5, 2, 3, 0 represents some point. And plus R times this vector means we're going some distance in this vector's direction. So you've got some vector or some point representing these coordinates in X, Y, Z, W 4-dimensional space, plus any multiple of this vector. If you can go as far as you want in that direction or the opposite direction if negative, you get a straight line. So all the solutions to that system of equations will form some diagonal straight line in a 4-dimensional universe. So that gives us a geometric interpretation of the results. If you were to graph those 4-dimensional surfaces, their intersection would be a straight line. Any other questions on that? All right, that's all the time we have for today. But again, try this out, get some more practice. You can apply these methods to any system of linear equations. So pull up any system of equations you've got, whether it's notes from high school or from a previous math class, or even just look online for system of equations practice. This method should work for any system of linear equations. If it has a solution, this will find it. So give that a try, and I will see you next time.
Thank you.
You're welcome.